So now the third case is there's three different indeterminate power, and that's, where we're going to have a function where we're finding the limit of one function raised to another function. So that's going to lead to these three indeterminate power forms that we can use L'Hopital's on. So if you think back to differentiation, when there was a function in an exponent, we would use logarithmic differentiation because that's how we get it out of the exponent and we turn the power into a product. So we're going to do that again. What we're going to do is we're going to assign a variable to the expression we're taking the limit of, f of x to the g of x power. We'll take the logarithm of both sides, and it doesn't really matter which one, but we take ln. Just for convenience, remembering it's base e. And then using that the power rule of logarithms, ln of y turns into this, g of x times ln of f of x. So if you look at this, this could be of one of those three forms, because g of x, if it was 0 to the 0, that means that the limit of g of x goes to 0, and the limit of the ln of f of x would go to minus infinity. So then this would be of the form 0 times infinity. Likewise, if this were of the form infinity to 0, then when I express it as a product, it's of the form 0 times infinity. And then lastly, if it was of the form 1 to infinity, then when I express it as a product, it's also going to be infinity times 0. So it doesn't matter which of these three indeterminate power cases it is, we're going to do the same thing. And we're going to look at that procedure in the next slide. First example of these other indeterminate forms. So the limit as x goes to 0 from the right of x to the square root of x. So this is of the form 0 raised to the 0. So again, this is an indeterminate form, but what we're going to do is use the logarithmic procedure here. We're going to set y equal to this expression, x to the square root of x. We're going to take the logarithm of both sides and use that power rule of logs so that we have this product. So now that we're going to take the limit of both sides of those, the limit of the ln of y and the limit of this product. So this is in that 0 times infinity form. So we need to rewrite it using L'Hopital's. So if we rewrite the square root of x times ln of x as ln of x over 1 over the square root of x, then the limit as x goes to 0 from the right is going to be of the form infinity over infinity. So we can use L'Hopital's now that we've put it in this form. So we can differentiate the numerator and denominator, and I end up with the limit of 1 over x over minus 1/2 x to the minus 3/2. So if I simplify that a little bit, I end up with the limit as x goes to 0 from the right of minus 2 times the square root of x, which is just simply equal to 0. But we're not done yet, because remember, we took the natural log of y. We've found the limit of the natural log is 0. This is a limit of the logarithm. We need to find the limit of the original problem. And we do that by remembering that you can always express any value as e raised to the ln of that value. So what I'm going to do is I'm going to go back to my original problem. So I have the limit as x goes to 0 of x to the square root of x. And remember that you set that equal to y. So I'm replacing that the limit as x goes to 0 of y. And I'm replacing that with this identity. So it's a limit of e to the ln of y. Now I did find the limit of the ln of y was 0. So because that exponential function is continuous, I can bring that limit in here. So this is e to the limit of the ln of y, which we just found was 0. And e to the 0 is 1. A lot of things involved in these steps. The logarithm of both sides, rewriting it so that it can be used in L'Hopital's, doing L'Hopital's, then remembering that you need to re-express it like this because you found the limit of the logarithm, not the limit of the original problem. So we have these other indeterminate forms, infinity to the 0 power and 1 to the infinity. Again, it's a matter, these aren't really the values that we're talking about. We're talking about functions that approach these values. It just depends which is approaching more quickly, which has the greater influence as we take the limit. So for another example, there's as x goes to infinity of x to the 1 over x. So here the base is growing without bound, so this x is going to infinity, and 1 over x, that function would be going to 0 as x goes to infinity. So I have this case, infinity to the 0 here. So we'll use that same procedure before and use L'Hopital's rule. So we do those 6 steps. We set y equal to the expression in the limit. We take the log of both sides. We use the product rule for logarithms. So this is of the form 0 times infinity. So we're going to rewrite this so that it's a quotient and meets the criteria for L'Hopital's rule. So if I rewrite 1 over x times ln of x as ln of x over x, that's pretty easy. This is infinity over infinity. Now we use L'Hopital's and differentiate the numerator and denominator. And taking that limit, I get 0. So now I need to remember that was the limit of the logarithm, not the limit of the original problem. So substituting e to the ln of y for y, I get e to the 0, which is 1. So that is the answer to the limit as x goes to infinity of x to the 1 over x. And then my last example of the other indeterminate form is of the form 1 to infinity. So you can see that this is an example of as x goes to 1, the base is going to 1, that exponent is going to 1 over 0 or infinity. So again, using the same procedure, y equal to the expression, take the logarithm of both sides, and I have it in the form 0 times infinity. So I'm going to use L'Hopital's rule, and if I rewrite this as the ln of x over 1 minus x, then it's of the form 0 over 0. And I can use L'Hopital's and differentiate numerator and differentiate the denominator. I get minus 1. So my last step is to find the original limit by substituting e to the ln of y equals y. And I get that is e raised to my limit I got here is e to the minus first, which is just 1 over e.